All right, we've talked about limits as we approach a hole. Remember, even though there's a hole, we can still have a limit there, as long as we're together, right? So let's talk about what happens then if there's not a hole, but possibly a vertical asymptote. You've heard of vertical asymptotes before, right? It's a vertical line that your graph gets close to but doesn't touch. So imagine you have a vertical asymptote in your function, in your graph. What are the possible behaviors as you approach that vertical asymptote? Well, as you approach it from the left, could you go up? Or you could go down, right? And as you approach it from the right, you can go up or you can go down. So we have a couple different options. We can't ever hit that vertical asymptote, but it might shoot us up or shoot us down. Now, we're going to talk about that now. What happens when we evaluate a limit and we don't hit a hole, but we approach a vertical asymptote? My graph can do a couple different things. My graph can shoot up from the left and the right, and both of them go up. We would then say that the limit as x approaches that vertical asymptote, whatever that x value is positive infinity, because they're both going to go up, 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 up. Now, our graph can shoot down from the left and down from the right. So as we approach that vertical asymptote, they're both going to go down. We would then say that our limit approaches negative infinity. But if one goes down and one goes up as we approach that vertical asymptote, then we say that our limit does not exist. So we have a couple new things now. We've got to figure out then, when we evaluate our limit, are we going to hit a hole? And if we do, can we ignore that hole and figure out where we're at even though Starbucks is closed because our limit still exists? Or are we hitting a vertical asymptote? Because if we're hitting a vertical asymptote, then we only have three options. We're going to go up, up to positive infinity. We're going to go down, down to negative infinity. Or one's going to go up and one's going to go down and our limit doesn't exist. Only three options. But we have to be able to tell the difference between approaching a hole and approaching a vertical asymptote. So when a function increases or decreases without bound, you hit a vertical asymptote and you keep going up or you keep going down. This limit technically does not exist or fails to exist. But I don't want you to stop there. I don't want you to say just because there's a vertical asymptote in our way, the limit doesn't exist. I want you to say, well, does it just go up to positive infinity? Does it just go down to negative infinity? Or does it really not exist? So technically, if you say the limit doesn't exist as you hit a vertical asymptote, you're not wrong. But I'm going to ask you to go a little bit farther. I'm going to ask you, does it just approach positive infinity, negative infinity, or does it truly not exist? Okay? Now, we're going to know that there's a vertical asymptote when you get a number over 0. Anytime you have a function where you have a value on the top and a 0 in your denominator. Remember that zeros in my denominator are undefined. In our function, that means there's a vertical asymptote there. So after you've crossed off the holes, remember we talked about that in the last video, where if you factor the numerator and the denominator and there's something that crosses off, you've just found a hole. But if there's something left over that's going to cause your denominator, your bottom, to equal 0, well, that number then is going to be a vertical asymptote. And that's a little bit different than a hole. So if it crosses off, it's a hole, then you can figure out where your hole is at and if we're together at Starbucks. Or is there a vertical asymptote? Is there a number on the bottom that's going to cause a 0 that's not a hole? Then if it's a vertical asymptote, we're either going to go up, up, we're going to go down, down, or our limit is truly not going to exist. All right, let's look at example number 3 so you can figure out what the heck I'm talking about. Example number 3 says, find the limit as x approaches negative 2. Now, I don't have a picture, and I don't have a table of values. All I have is an equation. I can try to factor it and see if there's any hole. Can't really factor the numerator. I guess I could factor our GCF, a 2, out of the denominator. But you notice that there is no common factor. Nothing in the top can cross off with anything on the bottom. Remember, whole pieces, whole factors have to be reduced. You cannot just cross off the 2's because they're connected with a plus or minus sign. So because there's not an x plus 2 only at the top and an x plus 2 at the bottom, there is no factor that can be canceled, which means there's no hole. But my denominator could possibly equal 0, right? If I were to set this piece equal to 0, then what can x not equal? Because that's going to cause our denominator to be 0. Well, x equals negative 2, right? If x is negative 2, then I'm going to have a 0 in my denominator, and what that means is there's actually a vertical asymptote at x equals negative 2. Well, unfortunately, that's what we're trying to figure out. What happens as we approach -2? Well, now we know that there's a vertical asymptote at -2. But that's kind of good, right? If we know that there's a vertical asymptote at -2, well, now we know there's only 3 options. As we approach -2, that vertical asymptote, we only have 3 things to do. We're either both going to go up and approach positive infinity, we're both going to go down or approach negative infinity, or one's going to go up and one's going to go down, and our limit truly isn't going to exist. But I only knew that because I knew that there was a vertical asymptote at x equals -2. So we're going to do a couple different ways right now. We're going to do graphically, and then I'm going to have you look at a table of values numerically. Now, graphically, I just put this in my calculator. I went into my y equals, and I put in my 3x plus 2 and my 2x plus 4, making sure I put parentheses on both the top and the bottom. I then looked at the picture, and it looks something like this. You notice that there's a vertical asymptote at -2. That's what we said, right? As I approach that vertical asymptote from the left, it looks like my graph shoots up to the sky. But as I approach that vertical asymptote from the right, it looks like my graph shoots down to the ground. So what would you say the overall limit is as we approach -2? Well, if you're going up and I'm going down, we're not going to be together, so our limit truly does not exist because we've hit that vertical asymptote and one side goes up and one side goes down. But I only knew that because I looked at the picture. So what if we took away the picture and we did a table of values instead? We used our calculator, we punched this into our y equals, and we did the table of values. We plugged in numbers really close to -2 from the left and really close to -2 from the right. So here's an example of that. You can punch in numbers close to -2 on the left and close to -2 on the right. What happens with your y values? Well, it looks like they go from 21 to 201 to 2001 to 20,001. It looks like these are getting really big really fast, right? But if you look on the other side, we have -18, -198, -1,998, and -19,998. It looks like these are getting really negative really fast. So it looks like these are getting really small really fast. This is getting really big. This is getting really small. And if there's a vertical asymptote here, well, then I can say that my limit truly doesn't exist because this is going up to positive infinity and this one's going down to negative infinity. So I can do a table of values to evaluate my limit, or I can look at the graph to evaluate my limit for right now. We'll talk about how to do it without either of those in a little bit.